The solutions of a linear inequality in two variables can be represented on a coordinate plane by shading a region on one side of a boundary line. For example, the solutions of the inequality y is greater than or equal to x plus 1 are represented by the red shaded region of the coordinate plane shown. In this case, the boundary line is the line y equals x plus 1. Now, to understand why all the points in this red region represent the solutions of the inequality, let's look at a particular example, the point -3, 4. We can see that if we substitute the coordinates of this point into our inequality, we would obtain 4 is greater than or equal to -3 plus 1. That's clearly a true statement since 4 is greater than -2. That indicates that the point -3, 4 is a solution of the inequality. And if we were to select any other point from this red region and substitute its coordinates into the inequality, we would see the same thing happens, that that point makes the inequality true and therefore it's a solution. On the other hand, if we select a point from the unshaded region of the coordinate plane, such as 1, -2, and substitute its coordinates into the inequality, in this case we would obtain -2 is greater than or equal to 1 plus 1, which is false because -2 is not greater than or equal to 2. Since these coordinates did not make the inequality true, then this point is not a solution of the inequality, and all the other points in this unshaded region would have the same effect. It's important to note that in this particular inequality, points on the boundary line, such as 2, 3, are solutions of the inequality. Let's use that example and replace the x and y in the inequality with those coordinates. We would obtain 3 is greater than or equal to 2 plus 1. Now, since 3 is equal to 3, then this is a true statement. And so all the points on the boundary line are solutions of the inequality, and we indicate that by drawing the boundary line as a solid line. So let's talk about the steps for graphing an inequality on the coordinate plane. First, we're going to graph the boundary line. If the inequality contains a greater than or equal to or a less than or equal to symbol, then that means the points on the boundary line will be solutions of the inequality. And therefore, we will draw the boundary line as a solid line. On the other hand, if the inequality contains greater than or less than, then points on the line are not solutions, and so we will draw our boundary line as a dashed line in those cases. Secondly, to determine which side of the boundary line should be shaded, we can simply test a point in the inequality. And if that point makes the inequality true, it's a solution, and we can shade all the points on that same side of the boundary line. If that point makes the inequality false, then we know that those points on that side of the inequality are not solutions, and we'll shade the opposite side. Now let's do some examples. Our first example is to graph the solutions of 2x minus 3y is greater than 6. In this case, the boundary line would be 2x minus 3y equals 6. It's relatively easy to graph this line by identifying the intercepts. If we first let y equal 0 in this equation, then we would have 2x equals 6. So the x-intercept is the point 3, 0. We can plot that point on our coordinate plane. On the other hand, if we let x equal 0, then we have the equation -3y equals 6, which means the y-intercept is the point 0, -2. We can plot that point on our coordinate plane as well. Notice that we have a greater than sign. This indicates that our boundary line should be a dashed line, because points on the boundary line will not be solutions to this inequality. Finally, we need to determine which side of the boundary line should be shaded. So let's use a test point. Often the origin is a nice convenient point to use because we can easily substitute the coordinates 0, 0 into our inequality. In this case, we would have 2 times 0 minus 3 times 0 is greater than 6, or 0 is greater than 6. Since this is clearly a false inequality, the origin is not a solution, and neither are any of the points that fall on the same side of the boundary line as the origin. So we're going to shade the opposite side of the boundary line, this sort of lower right-hand region, because this must be the area of the coordinate plane that contains the solutions of the inequality. Let's look at a second example. In this case, our inequality is y is less than or equal to negative 1/2 x plus 3. So the boundary line would be y equals negative 1/2 x plus 3. This is written in slope-intercept form, so we can see that the slope of this line is negative 1/2, and the y-intercept is the point 0, 3. So starting from that y-intercept of 0, 3, we can count down 1 and to the right 2 and find more points using the slope. And then we can connect those points to form the boundary line. Notice that we have a less than or equal to symbol. So we're going to draw this boundary line as a solid line, indicating that the points that fall on the line are solutions of the inequality. Finally, we can use a test point to determine which side of the boundary line should be shaded. Once again, let's use the origin, since it's simple to use. In this case, the inequality would read 0 is less than or equal to negative 1/2 times 0 plus 3, or 0 is less than or equal to 3. That's clearly a true statement, so the origin is a solution of the inequality, as are all the other points which fall on the same side of the boundary line as the origin. So we will shade that side of the coordinate plane to indicate the solutions of the inequality.